Thank you. Thank you, everyone, for joining, and I appreciate the opportunity to speak with you today. And yes, my name is John Swanson. I am the Director of Finishing at MacDermid Alpha. So as Haley said, I'm going to take approximately 30 to 40 minutes to talk to you today about circuit board finishing technologies and choices. So I'm progressing my slides now, Haley. I assume you can see it. And
Yes.
This first slide here is just a simple summary to talk about some of the common finishes. OSP, immersion silver, immersion tin, nickel gold, ENIG as we simply call it, and ENEPIG. You can see a simple color code here that we want to communicate that none of the finishes are perfectly strong. Each has some strengths and weaknesses. So today I hope to be able to talk about some of the strengths and weaknesses, the considerations you may have as a fabricator or as a user of circuit boards or as an assembler of circuit boards. Over here on the right side, we generally just give some general ranking for the use of circuit boards by surface area. From if we look at surface area of circuit boards, the most used surface finish is OSP, and perhaps the least used is ENEPIG by surface area. But there's many more specific choices and issues that you would consider when choosing a finish for your application. So I hope I can help today give some insight as to some of these strengths and weaknesses and details for each finish. When you consider a surface finish, before we begin talking about the surface finishes, we want to just simply mention that the assembly operation is something important to consider when you think about what surface finish might be the best choice for your application. So here on the right side of this slide, and I'm highlighting with my pointer, we've simply shown two basic profiles of assembly reflow cycles. One we call a standard cycle. Another, we generally refer to it as an IPC cycle, but there's many names, there's many different cycles. The point of my communication here is to highlight that when you're thinking about a surface finish, you should think about the application, the assembly application. You should think about the number of exposures to assembly cycles that the finish will see, and you should think about the specifics of that cycle. Here we show a peak temperature. Something to consider is the peak temperature of the cycle. Something else to consider is the whole profile of temperature. This IPC cycle is a little bit more aggressive, with this red area here that we show as a high shoulder with higher temperature. And this can be more aggressive and more challenging to the circuit board finish. So I'm going to walk through some basic considerations for the finishes. And over here on the left side of this table, we talked briefly about the coating thickness, maybe some particular detail on the coating process. How does the coating change? How does the surface finish change when exposed to heat and time? So we just want to note that, the soldering mechanism, and some very quick detail on the solder joint. So the first item here is OSP. OSP is an organic coating. Thickness is about 0.3 microns. It's a family of organics called azoles. So the specific organic coating will vary depending on the chemical vendor, but it will be categorized in a family of similar organics called azoles. The organic can degrade over time if it's exposed to heat. There will be some degree of breakdown in that coating. We're going to talk about each finish in more detail, but this is just a basic quick summary. So if we think about immersion silver, the immersion silver coating is about 1/4 of a micron thick. It's immersion plating. I'll get into that in a few moments of explaining why I mentioned immersion. The there's minimal oxidation with heat and time for the immersion silver coating. And when we solder that coating, the silver rapidly dissolves in the molten solder, and you form a tin copper solder joint. Next coating we just briefly mentioned here is immersion tin, a little bit thicker, 1 micron. It's again immersion plating. We have a thin tin oxide and tin copper alloy growth over time. So when the immersion tin is exposed to heat, and when it's if it sits in inventory in a hold period, there is a slow growth of alloy or intermetallic between the tin and copper that grows over time. We have tin dissolution in the solder, and we have a tin copper solder joint. And briefly, I'll mention ENIG and ENEPIG together because of their similarities. For the nickel, we typically have 3 to 6 microns in thickness of nickel. As you see here, I have a highlight saying there are some specific applications out today where thin nickel is used. In certain situations with, for example, high frequency RF applications, we see some choices of thin nickel, but basically the most common is the 3 to 6 microns of nickel, followed by, in the palladium case, 0.05 to 0.3 microns of nickel, of palladium, and a very thin gold top coat or top finish. And here we have electroless plating and immersion plating, and I'll just briefly mention that generally speaking, electroless plating is a bit more complex, a little more challenging from a process control standpoint. Immersion plating is a bit of a simpler process where we have a displacement reaction of, for example, in the case of silver, as an example, you have a silver displacing a small amount of copper, and it's a fairly straightforward, quick reaction. So generally speaking, the electroless reactions are more complicated or a little more challenging, a little more complex, posing a little more challenge to process control. The difference with ENIG and ENEPIG is we have rapid precious metal dissolution, but then form a tin nickel solder joint with the tin-based solder alloys. So moving forward, I will spend some time today walking through and talking briefly or spending a little bit of time on each of these finishes. So I'm going to start with OSP. It's a low-cost finish. Of all the finishes, one of the benefits of OSP is it's very low cost, no precious metal, less cost. It's the most used surface finish when we're considering, if we think in terms of PCB surface area. It's a benzimidazole-based coating, and there are some limitations linked to electrical contact performance, but it does inhibits oxidation of the underlying copper and is a very good fundamental finish for basic applications. So if we think a little more about some of the details of an OSP coating, it's just some of the considerations when thinking about optimizing a coating. We have an organic on the surface. Not all of the OSP coatings are precisely or exactly the same. There is some difference in that organic molecule from each vendor, but basically, as you consider that coating, we want to think about how stable is the chemistry. Is it easy to use at the PCB fabricator site? Are we able to build thickness readily? What's the permeability to air? So it's the basic, as the name says, the basic mission of that coating is to serve as a solderability preservative, so to protect the copper surface from oxidation. We're trying to design a coating that is stable, choose an organic material that can sustain itself through those assembly operations. And lastly, we want to think about a coating that is compatible with the subsequent assembly steps. So it's compatible with various fluxes and pastes that will be used in the assembly operation. I look here at the process cycle, or the basic process of producing an OSP coating. We start with a circuit board with a unfinished copper surface. and we want to clean that surface. We're going to micro etch that surface, get the residues off, get fresh copper. And in some operations, we perform a pre-coat followed by the OSP coating, rinse, and dry. And this whole cycle takes about 15 minutes. I show a photograph here of a horizontal circuit board line. This can be done vertically, but in more production environment, a higher production environment, it's more common to have a horizontal machine processing circuit boards through this line in a conveyorized manner. So I'm going to spend a little time now to just walk through the coating mechanism and the assembly mechanism. So if we consider this illustration, we're starting with a copper pad, clean that copper pad, micro etch it. We remove a small amount of copper in the micro etch step. And then we prepare that surface in some cases with what we call a pre-coat, just to basically lay down a very small layer of organic to prepare it for the subsequent OSP step. So that's basically, let's consider that step one. So we have an OSP, or we have a copper surface with this pre-coat that's been cleaned and etched. So the next step is to apply the OSP coating. So we're just illustrating that in this drawing here. We're putting down the azole-based organic coating. So we have an organic that forms a bond with the copper surface and is able to build some thickness to approximately 0.3 to 0.5 microns thick. So we build the organic coating. The organic coating has a reaction to form a bond with the underlying copper. So our objectives, the objectives of the OSP, we want to be thermally resistant. We want a coating that's able to endure 1, 2, perhaps 3 multiple heat cycles in assembly. We want to protect the underlying copper surface from oxidation, and we want to be compatible with solder pastes and fluxes. Now I'm going to move forward, talk a little bit about the reflow and assembly operation. So we have a coating that's applied, and the PCB is now ready to have the solder paste printed. So I'm illustrating here, if we're printing the solder paste, I'm showing this with my highlighter. If I look over here on the right, what we're trying to communicate here is that the solder paste is really a mixture. The solder paste is a mixture of metal, solder metal, and in this red area, solder paste includes flux and activator chemistry, which has a role to work with the OSP to ensure good, effective, optimized soldering. So if we start, as we show here, to start the reflow cycle, as we start to heat the board or the assembly in a assembly cycle, the first thing that happens as the heat builds is the flux over here, the flux and activation chemistry begins to attack the OSP coating. And as we progress through that, the attack continues, the heat builds, and we essentially, the paste chemistry dissolves and activates the underlying surface. You also may notice here that the paste begins to what we might call slump and prepare itself to melt for the assembly. So as that heat continues, we consume the OSP, we prepare that surface, and the reflow occurs. The paste melts, and we have a solder joint or a solder ball form. And as that progresses through the cycle, the impurities are evolved, and we form a tin copper intermetallic. And that walks through the basic cycle of an OSP. So what I've tried to communicate here is some of the key considerations that go into effectively using and considering and choosing and running an OSP process. So I'm going to spend now a little time on immersion silver. Immersion silver, I would say what is noteworthy about immersion silver is its simplicity. Very simple process. If you are a printed circuit board producer, it's one of the simplest, fastest, easy to use processes. The coating goes down quickly. in about 1 minute. And the coating here, as I'm showing, is very durable to multiple reflows. Good electrical performance, and later we'll talk a little bit about performance at high frequency. So here's another description of the process cycle of coating silver. So we clean, similar to OSP, the basics are similar. Clean, we micro etch, we have a short pre-dip, and then the silver plating step. Short cycle here, 12 minutes, a bit of a shorter line, simpler line, and a straightforward process here where we have silver ions, copper metal, underlying metal, and some of the copper metal in an immersion reaction is dissolved, and the silver coating as metal goes down in place of the small amount of dissolved copper. So that's the basics of how this proceeds, and about a 1/4 micron, a little over a minute coating time, and the whole cycle time is quite short. So it's one of the things to take away here, this messages is it's a simple, straightforward process. This slide is meant to help communicate that silver is unaffected. This is one unique part of silver. It is unaffected by exposure to many heat cycles. OSP sees some degradation of the organic coating. Immersion tin, as we will talk about later, has some problems with building an intermetallic alloy when it's exposed to reflow cycles. But silver basically has no significant reaction. These are wetting balance curves that show the performance in a solderability test. And you can see as a coated board behaves very similar to a board that's been through 2 reflows, and it performs very similar to a board that's been through 4 assembly cycles. So this is the preconditioning, and it's simply showing that the performance of a board is largely, mostly unaffected by many reflow cycles. That's the basic message of this slide. Silver has been used in some new applications. You may, as you study the industry, you may see in our electronics industry some subjects of interest right now involve performance of electronics at high frequencies. That includes things like 5G applications. It includes things like driver safety systems in more advanced automobiles and cars. So silver has performed well in these applications. I'm showing a picture of a couple antenna high frequency applications that in this case happen to be in automotive applications, one at a moderate frequency of 24 gigahertz and another at a relatively high frequency of 77 gigahertz. And so one of the strengths of silver is its performance at high frequency. I will here move to another slide, and I'll take a moment to explain this slide. This was a paper presented by Rogers Corporation. I highlight their credit, their authorship of this paper here. Rogers published this paper and talks about the performance of different surface finishes shown here across various frequencies. So I see my pointer looking at the horizontal axis and frequencies, and the vertical axis is loss. So this is signal loss. So we like to see less signal loss, so less movement from 0. So the better performance here are these blue lines, which is bare copper, immersion silver, and OSP. The bigger, larger amount of signal loss occurs with the other finishes. So this is one reason why some designers have chosen immersion silver as a finish for high frequency applications. As you can see, there's less signal loss at given high frequencies. The reason for that is somewhat complex, but basically I will summarize the basic reasons. Here over on the left, we see skin depth. This symbol here is a representation of skin depth. And one key element that we want to think about as frequency goes up, the skin depth goes down. So as you have high frequency applications, the current in the circuit will travel, the electrical current will travel through this, what we call the skin, closer to the surface. And in those situations, the high conductivity metals are more desirable. So silver and copper are more desirable if the current is traveling near the surface where those metals are. Lower conductivity metals such as tin and nickel will not perform as well. Now, this doesn't apply to many applications. This is a niche subject, but it is something that has driven some use of silver in our industry in the last few years. Another factor that must be considered with silver involves tarnish. If silver is exposed to the environment in ongoing use, it will form a tarnish. The tarnish can be inhibited through post-treatments. So these post-treatments can be durable and endure heat exposure in assembly. So with some degree of post-treatment, things like basic tarnish, which is a very thin layer of silver sulfide and copper sulfide on the surface, can be inhibited. Now, there are more extreme types of corrosion that can happen with exposure to sulfide and acid gases and humidity that present some risk with silver. So we want to be clear that silver in some excessively polluted environments with high sulfide levels, high H2S levels, and humidity can be a problem. And this is one of the limitations of silver. We can stop basic tarnish, but aggressive forms of corrosion that can occur in highly polluted environments can be a concern. Now I want to move on to immersion tin. Immersion tin has a moderate cost versus the other finishes. It's highly used in the automotive industry. It's not used in many other industries, but if you look at where immersion tin as a surface finish is used, well over 50%, easily 60+% is used in the automotive industry as a final finish. I'll highlight these red areas here, and this is the weakness of tin. The weakness of tin is that when the tin coating is exposed to an assembly cycle, the tin coating will form a intermetallic, or we might say alloy, with copper. And that intermetallic, I'll show in a subsequent slide, is less solderable. So we want to find ways to inhibit that and make sure that we can build enough tin thickness to preserve free tin as the circuit board is exposed to multiple assembly cycles. The tin cycle is shown here. So similarly, a cleaner, a micro etch, and a pre-coat. One point I want to make here is that the tin chemistry is generally, among all the significant vendors, is a hot chemistry. Chemistry runs approximately 70 degrees Celsius. And that can have some aggressive effect on solder mask. So sometimes what we call a UV bump is done, where some energy is delivered to the solder mask to further cure it and prepare it for exposure to the hot tin plating chemistry. This is an immersion reaction, so it's fairly simple. Not quite as simple as silver, but quite relatively straightforward, where we have copper dissolved into the chemistry and replaced by tin. So we call it a replacement reaction or a displacement reaction, or you could call it even a corrosion reaction, where you're corroding the copper in a controlled way. Some copper enters your chemistry and the tin is deposited on the circuit board. And the cycle here is about 20 minutes. So I would call this moderately complex when compared to simple processes like silver and OSP. Immersion tin plating is aided by a complexing agent. So if we consider displacement or immersion reactions, I show one example here is silver is a more noble metal than copper, and it will naturally, very easily and straightforward, will displace the copper and plate onto the copper surface. Tin is not a more noble metal than copper, so normally it would not easily plate in an immersion reaction onto copper. However, all of the major chemistries that are used today utilize a complexing agent. It's typically thiourea, but it's a complexing agent that enables this reaction to be reversed. Basically, it reverses the reaction and enables tin to displace copper and plate onto the copper. So this is one of the reasons that the immersion tin reaction or the immersion tin process is a little bit more complex than, say, the immersion silver process or even the OSP process. Now, I talked a little bit about this intermetallic. So, and again, if I just quickly go back and I say the board is limited in its ability to go through reflow cycles. It can go perhaps through 2, and it's at the 3rd step, it's really challenged. So to explain that a little more, the industry standard is to have a micron of copper, or I'm sorry, a micron of tin here onto the copper. There's a thin layer of tin copper intermetallic alloy, and in some cases we may build up to 1.5, but the industry standard is around 1 micron. Now, when that 1 micron of tin is exposed to one reflow cycle that I show over here on the right, what happens is that tin is consumed and a tin copper alloy grows. And as that process continues, if it's exposed to a 2nd or even a 3rd heat cycle, the pure tin is consumed entirely, and the ability of that circuit board to solder and assemble effectively is lost. So these are some curves that are measuring these flat areas. This is an electrochemical curve that shows the amount of free tin. I'm highlighting it with my pointer. This area is the intermetallic, and this is the base copper. So you can see the free tin cycle is lost. So the main message is shown in these illustrations is that as we go through a heat cycle, the pure tin is lost. So our challenge is to be able to plate pure and free tin that is free and ready to effectively solder in any assembly operation. Another consideration for tin is whiskering. And whiskers will form as a SEM photograph of a whisker. Here's a microscope photo of a whisker inside of a through hole. Whiskers can grow on tin coatings, particularly pure tin coatings that are plated on copper. It's a response to stress. And so our basic mission or our basic objective is to reduce stress. For most of the chemical processes that are offered in the industry, this is done through the addition of a small amount of an alloying element, very small amounts of a secondary metal. Those are delivered through an additive, and those have been proven to be quite effective. These are some graphs here that shows by using these additives, we can very effectively reduce the amount of whiskers from a process. So I would say that the risk of whiskering from a process that's run effectively is quite low. Next, I want to move on and talk about nickel gold and ENEPIG. So these share the EN operation and the IG, the nickel and the gold. So I'm going to talk about these together. And these are higher cost finish for obvious reasons because of the inclusion of the precious metal. They're often deployed and used in very high value and high reliability applications. Smartphones in some applications, some of the smartphone surfaces on a board are nickel gold or nickel palladium gold. Many medical and aerospace applications in order for higher reliability due to the protection that's offered through the gold and palladium utilize those processes. Now, these are electroless chemistries. So what I tried to communicate earlier is that these processes are a little more complex, a little more challenging for the circuit board fabricator to run. They require a bit more process control, a little more attention, a little more service. ENEPIG here is primarily used in wire bond applications. So from modern gold and copper wire bonding applications, ENEPIG is the preferred choice. Now there's some renewed interest in the industry linked to EN corrosion. I'm underlying that here because I'm going to spend a little bit of time today talking about this matter related to corrosion. So if we think about the process, it's a longer process. It is more complex. Here's a photograph of a ENEPIG line. ENIG and ENEPIG would look similar. These are vertical rack plating operations. So I'm showing that these are various tanks, and a rack plating would transport circuit boards through these various tanks in the operation. We go through a clean etch and activation similar to the other processes. I'm going to spend a little time here just to note that electroless nickel will not, as I'm highlighting, electroless nickel will not plate directly onto copper without some catalysis, without catalyzing the surface. So the way we typically do that is through palladium. Very, very, very small amount of immersion palladium on the surface just to serve as a catalyst to enable the electroless nickel to coat the surface. Moving forward to the next step is electroless nickel plating. This is about a 20-25 minute operation. Within the full operation, we're depositing a nickel phosphorus alloy. We're utilizing reducing agents in the chemistry. In this case, we're showing hypophosphite as a reducing agent. This delivers some electrons to the nickel to reduce the nickel in solution and allow it to plate on the surface. Electroless nickel will deposit a nickel phosphorus alloy, and we can vary that alloy from typically somewhere low percent, around 5 or 6, to a higher percent to perhaps 12%. The higher the phosphorus level, the higher the corrosion resistance of the nickel deposit. The higher the phosphorus level generally, the more challenging it is to put down the subsequent gold deposit. In the electronics industry, we do see a range, depending on the application, of EN electroless nickel from 5, 6, up to 12%. The gold operation is an immersion reaction. So we have a mixed system with an electroless and an immersion reaction where the gold displaces the nickel to form the final step on the ENIG coating. Now, I do want to spend a little bit of time talking about corrosion. Some of you are surely exposed to IPC. There are committees formed in the industry today studying and working on specifications linked to corrosion. The IPC has a committee called 4552. They're working on this subject. Basically, they're attending to matters related to gold thickness and the mechanism of corrosion. They're studying the underlying electroless nickel because the electroless nickel and the phosphorus content have a relationship to corrosion. Higher the phosphorus content, generally the more resistant to corrosion. And there's some work and attention paid to the tools used in a laboratory or in a process control environment, such as thickness measurement tools, and their ability to participate in process control. So, for example, X-ray fluorescence, XRF tools have advanced and are now able to more accurately measure the phosphorus content of a nickel coating. They were more accurate in their ability to measure thickness distribution on a circuit board. There have been some revisions to the IPC work that's still going on. And to keep it simple for this shorter meeting, there are levels of corrosion, level 0 being very good, level 1 basically being good. And there's some work going on right now to describe precisely what we call level 2 and level 3 corrosion. But I'm going to show pictures of that corrosion in a moment. And again, the corrosion really comes back to this reaction, the gold going down on the nickel surface. So here are some pictures to show some basic forms of corrosion. Here we're showing a good example where we have the underlying copper and the nickel gold coating, and we don't see much of anything here. There's no corrosion showing, very little corrosion. This is a cross-section photograph of the gold over the nickel over the copper. On here, on this, what we call the knee of this hole, you can see some significant corrosion. And if we take a microscope picture of that, we can see more clearly this corrosion. And that occurs when the gold chemistry is attacking the underlying nickel. So this is, again, some attention in the industry to this subject at this time. A related subject has to do with gold thickness control. And I believe I put 2 slides in here where I'm going to go right to the second slide. I had one more slide than I planned. But basically, if we look at a circuit board surface, you will know that there's many types of features on a circuit board surface. And these features vary. For the bigger features for an immersion coating, it's common to have thinner deposits to large features, as I'm highlighting here. And it's common to have thicker deposits on small features. For example, this BGA has these small features. It's common to see thicker deposits from immersion systems on the small features and thinner deposits on the large features. This can play a role in a customer or a board fabricator meeting specifications. So what we want to do is measure the distribution. I'm showing in simple bell curves here, but the simple distribution of the gold thickness on a board across the whole board, across all the features. So you can see in the blue trace here, we're looking for or describing a very good and highly controlled distribution. And in this yellow to brown color, we see a more common wide distribution. And the problem with this can be that the spread can go below a specification, and in high cases, it can also produce increased corrosion. The other concern is if we move that distribution up, then our cost, our mean, our average cost of the precious metal goes up. So these are areas of concern that also relate to corrosion. This was a quick case study. This sample here is more of a simple illustration. And here we're looking at a distribution of gold in this series of data. We're looking at many samples across the lifetime of a chemistry. So the chemistry will have a lifetime as it works from being a fresh chemistry to being an extremely overused chemistry. And the challenge is to maintain the process through the lifetime of the chemistry at a level that's within the specifications shown from high to low. So one final step here. Now I'm going to briefly talk about ENEPIG. Palladium thickness can range from, I'm often thinking micro inches, 3 to 10 micro inches, so up to 1/4 of a micron. And it is an electrolysis reaction similar to electrolysis nickel, a bit more complicated, a bit more complex, and used again in wire bonding applications. Gold reaction, the gold displacement, the gold immersion is really almost the same for both ENIG and ENEPIG. In reality, we think that, and it is common to think that the palladium is a barrier between the gold and the nickel, but it's important to realize that the palladium is quite thin, and much of the reaction between the gold really is occurring with the nickel. So the corrosion really can occur at the nickel because the palladium is quite thin. There's much porosity. It is impractical. It is not realistic to have a thin palladium coating that is completely covering the nickel. So the reaction is really occurring with an underlying nickel. So just a few more slides before I wrap up today, but basically we would say, why do we care about nickel corrosion? And we give one example here of ball shear. So if we look at a ball shear situation where we put a solder ball on a surface and we push the solder ball off the surface and we measure the force required to do that, and we look at the nature of the failure mode, if we look at two processes, one that has high corrosion of nickel, because it's poorly controlled, we can create a process in which we see large amount of corrosion, and we can create a process which corrosion is well controlled. And if we measure the ball shear across many samples, we will see that the ball shear force is negatively affected, harmed, or hurt in situations with a high corrosion process. And we also can see that the nature of the failure mode, this area that I'm highlighting with my pointer, is not good. This over here, we see shear across the bulk of the solder. And here we see shear at the interface of the pad, which indicates some failure mode linked to the surface. So this is really one of the key reasons that the industry has some concern about corrosion in ENEPIG and ENEPIG applications. So my last subject today, before I take questions, is I want to highlight that there are some limitations of immersion gold technology. In the industry today, you may hear about other forms of gold technology. And what I want to show here is the nature of galvanic immersion coating. And we're looking at three situations: 5, 10, and 20 micron thickness, or micro-inch thickness of palladium. And the ability here to build gold thickness in those situations. So if I have a thin palladium thickness, I can build gold thickness over an immersion time quite easily. But if I build palladium thickness to 10 or 20, there is difficulty in building thickness. So the immersion gold system will have some challenges in ENEPIG situations. And you can see the photographs over here in all of these situations, each one. When we built up gold thickness, we see corrosion. The photograph, I hope for everyone can see, each of these has fairly severe, fairly bad corrosion. So the industry is looking at some other opportunities or some other potential solutions. We could call this a hybrid gold system. Sometimes you'll hear a system called a reduction-assisted gold system. And what is that? It's a system that combines a couple traits. It combines galvanic displacement or immersion and electrolysis properties or chemical reduction. So chemical reduction is another phrase might be electrolysis plating, and galvanic displacement, another phrase may be immersion. So the point from a hybrid system is a system that can do both of these, or has characteristics, we should say, of both of these in a single chemistry. And we want to highlight that this is being looked at in our industry now, and provide a little bit of guidance on why. And it really has to do with that corrosion mechanism. So as we look at the use of a gold chemistry over time, I'm going to highlight on this left chart. As we look at the use of a gold chemistry over time, we can see that gold chemistry will build up some nickel concentration in it Why will it do that? It will do that because it's corroding the nickel. So if we have a reduction-assisted or hybrid process, we will build that nickel more slowly. And with a immersion process, we will build that nickel more quickly. So this is just highlighting some of the traits. There are some risks with this, some risks with an electroless process that you could plate onto the laminate. So electroless chemistries are a little complicated, a little more prone to plate in areas that we don't want to plate. But with a well-controlled process, this can be controlled. On this side, we want to show, and this may be hard for everyone to see on their screen, but the ability for these blue hybrid system or the reduction assisted system to continue to build thickness for all palladium thicknesses. So for each thick and thin palladium situation, we can build gold thickness, but with the immersion system, we have difficulty. So that is shown here. The difference in the systems is shown here. So I believe I'm near my final slide, and to hopefully make a final point about these kind of systems, it's really focused on ENEPIG. If we look at corrosion, and if we were to measure corrosion from an immersion system in a challenging environment, and we were to take a photograph, you see this kind of more extreme corrosion. And on the left here, it's hard to see, I know, but we're looking at 10, 20, and 30 minutes of plating time in the immersion gold. So it gets worse, gets more challenging as we build this gold thickness. So we're showing 3 examples, 10, 20, and 30. If you're building gold thickness in this environment, it's challenging, and you can have corrosion in the ENEPIG system. Now, if I look at a hybrid system and I do the same type of challenge, we're able to show near zero corrosion. So the industry is looking at these. This is one of the very primary reasons why they're looking at it. You can see much better photograph here, really close to zero on corrosion. And that is because the reaction is mostly electroless. It's a mild, modest, low electroless reaction with a little bit of immersion. And that's what the reduction-assisted hybrid system represents. So this, I think, was my last slide. Thank you for your attention. I think I did go a little longer than I planned, but I hope this was helpful. There's a lot of material, and I'd be happy to take any questions now from the group. Thank you.
Hey, John. Thank you for the introduction of different final finishes. And actually take corrosion as one of the major concerns to introduce the difference and some possible mitigation approaches. Okay. So I see in the chat function, if you go to the chat as well, you also can read the questions there. There is a question from Jim Card regarding the OSP and the immersion silver. So his question is, those 2 finishes are preferred finishes for automotive high frequency, like 77 gigahertz radar applications. In terms of long-term reliability of exposed finishes, how do those these choices stand up to suffer contain atmospheres, humidity, etc.? Does OSP coating provide some level of protection in the application?
Yeah, it's a good question. What our experience is that in sulfur-bearing, humidity-bearing environments, there must be some additional measures taken. So in the automotive space, there are global OEMs and global tier 1 producers using immersion silver and OSP, and they've taken, in some cases, like the photograph I showed, they're taking these antennas and other systems and found ways to encapsulate them in their systems to give them additional protection. So both OSP and immersion silver require some form of protection in that way. They, are not designed as lifetime protection agents. There really have been solderability preservatives. But I can say if you do a teardown on some ADAS applications, some radar applications, you will find immersion silver, and you will find some innovative techniques for protecting those surfaces from real exposure.
Are there any other questions from the audience? You also can unmute yourself to speak out, or you can type in your questions in the chat.
This is Mark Kostinovsky, Schlumberger. If nobody has questions, may I ask multiple questions?
Sure.
Number one, about palladium. So what is phosphorus content in the palladium deposit?
It varies, actually. We have more than there's more than one process available out there. It can be in the low single digits, around 3 or 4%. Palladium is common. I'm sorry, is phosphorus is common. There are also pure
Mass
palladium.
percent or atomic percent?
Let's see. I believe it's mass percent.
Okay.
It's mass percent. That's a good. Boy. I believe so. I will check that, and if I'm quite confident I'm right, but if I'm wrong, we will come back to you. And there are also processes that are zero phosphorus. And in my opinion, you can have different opinions if you talk to different groups. We don't see a strong differentiation in performance in key areas such as solderability, solder joint performance, ball shear, wire bondability, etc. Some processes are, I'd say, easier to run and control for certain reasons, but from a performance standpoint, I don't have a strong opinion on one being superior to the other.
Okay, and since you're dissolving nickel under palladium, so that means you will have voids between palladium and the nickel. And third question is, when you solder to ENEPIG, obviously gold is dissolved, all right? So you are building only nickel tin intermetallics, or also palladium tin intermetallics?
We find a bit of palladium in if you go thicker with the palladium. I can. Your name is Mark, yes?
Yes.
Mark, I can share with you, offline or another time some interesting photographs of solder joints. As you build palladium thickness, you can find some palladium, and there's some reason to debate that higher palladium, once you get it, what I would say is quite high, costly levels, can impose some problems. Not at industry standard levels, but as palladium thickness builds, that could be a consideration. Now, back to your original point, of voiding. So I don't think of it as voiding, because when we have an electrolysis or immersion coating that is in the area of, let's say, 0.1 micron,
Spikes.
0.2 maximum micron, then that when you have 0.1, 0.15 micron, maybe 0.2, you really don't have a fully continuous surface. There is some amount of, shall I say, porosity or exposure to the underlying nickel. Now, maybe it may be fair to say spikes. But you have some displacement of that nickel. So yes, you have a little bit of preferential, maybe some, I guess you could use the word increase in voiding, but it's quite small, because the normal intent is to only put down, let's see, half a micron or 0.05 microns of gold, very, very small amounts. So this is, I agree with your comment basically, but it's at a very small level.
Okay, and I don't know if I'm asking too many questions, but gold, reducing agent for gold is also commonly used hypophosphite, or I'm asking for a trade secret?
Yeah, no, you're not asking for trade secret. It's overwhelmingly from all vendors that hypophosphite is the reducing agent. The differentiation among vendors really comes into relationship with stabilizers and some stability agents.
Mm-hmm.
All right, so the reducing agent is quite common. You will build up some impurity over time. So this is what happens with electrolysis systems. You build some impurity, and that system has it's somewhat dynamic. It changes as those reactions occur, and those chemistries must be dumped periodically. But from a nickel perspective, the differentiation has to do with control of the phosphorus. The differentiation also has to do with stabilizers that govern the rate of nickel deposition and its tendency to plate in a controlled way. So your question was not touching on proprietary measures.
Then I'm begging for one more question. When you do this deposition with the gold hybrid, right? Hybrid gold
Yes.
deposition. You obviously oxidizing hypophosphite, and are you saturating the surface of the palladium with the elemental phosphorus from that reaction?
Are you saturating the surface? No.
No, you're not reducing oxidizing hypophosphite to the phosphorus level, are you? Because palladium obviously forms with the phosphorus really nice intermetallic too. Well, you see what I'm saying?
No. Yeah.
Chemical compound, not intermetallic. Okay.
Yeah,
No?
that's a good question, but no, I don't think so. No, you know, the challenge in the hybrid systems is we're really creating a very mildly chemical reduction environment, where we could create, if we chose to, I mean, a poor system would be a system built on a very strong reducing agent. And the problem, of course, would then be that we would plate onto the tank walls and the filters and the laminate and everything. So finding a system that is only just with small amount of reduction capacity is the challenge there.
Okay. Thank you very much for your answers and your time.
Yeah, I'll be happy to answer more later if you wish.
Yeah, I'll find you.
Okay, thank you.
Thank you.
Okay, I think we are exceeding the hour. Just one last ask any other questions from audience before we close today's webinar? Yeah. Okay, if not, I think I would like to thank John again, and thank you all for joining. And we will provide the presentation slide and recording afterwards. Thank you all, and have a nice day and or nice evening. Okay.
Thank you all. Thank you, Haley.
Thank you very much. Bye-bye.
Thank you, John. Thank you, Haley. Bye.
Yeah. Bye.